So I'm going to talk about AI and sustainability. Let's try to put that together. So I'm Olivier Bierlaire. I'm very glad to be here in Dublin. It's been a while for me, and I see the weather compared to Brittany in France is pretty similar today. So as you might have read, I'm not working anymore at Elastic since last month, and I'm starting two projects. One, Carbonifer, for measuring the carbon footprint of cloud infrastructure, and Rebase.Green with some of the co-founders for reducing the carbon footprint of code in general, leveraging AI. So it's definitely right in the topic today. So let's talk about the pain of IT. So I might teach you something you might not know. Hardware is there to run software. If there is no software, no hardware. So the more you put on software, the more hardware you're going to need, and more energy it's going to use, and more CO2 it's going to emit for the production of this electricity. So we know that now IT is emitting more CO2 than civil aviation. Yes, more than flights. So everybody is worried about flights, and we might need to be worried as well for our IT. And by 2030, which is only in 6 years, IT is going to use 20% of worldwide electricity. So I know in Ireland it's around like 30%, I read somewhere. So it's start to be worrying. So it's not something like we can disregard. So why? There is this sentence that's been coined in the 90s: what Intel gives, Microsoft takes away. Basically, whenever Intel or any manufacturer is coming up with new hardware, new microchip, more powerful chip, the software is taking advantage of that. So maybe we can reverse that. Instead of upgrading our hardware, can we optimize the code so that we don't need to change the hardware? So this this infinite race needs to stop, basically. So let's talk about the elephant in the room, the Cthulhu. Make a joke. The legacy code. So what's the definition of a legacy code? So according to Wikipedia, is when the code is no longer supported on standard hardware. But most of us are extending a bit the definition of legacy code. And I like this one, which is code is legacy code as soon as it's written. Obviously, like in few months, part of the code is going to be obsolete, using obsolete libraries. You introduce some bugs, you have some flaws, and like whenever something can be done better, in my head is kind of legacy code already. So there is a couple of things that come with legacy code. Technical debt, we all know what it is. Bugs, obviously, suboptimal algorithm. Obsolete technologies, poor documentation, maintainability problem, and something people oversee is the loss of skill. Like after a while, the more a code is aging, the less you have people with the skill to maintain it. So it's kind of worrying. And everything has a cost, and legacy code has a cost. So shortage of skill, for example, means if you need to recruit someone to maintain your old code base in COBOL, you need to pay this person very well. And so there is another type of cost. I will not dive into that now, but there is some studies showing that for each line of code, there is $1.61 of technical debt with that. So it's a lot. And there is a waste of energy. So whenever we have suboptimal algorithm, whenever we don't have cache, whenever we are lacking of scalability, when we have like interpreted language, there is much more computing. And if there is much more computing, there is more electricity to run that computers, and you need to have more powerful machine, and you need to deliver and manufacture those machines. And at the end, it's more CO2 and more costs. So let's look more precisely to CPU. So it's something quite obvious, but I checked. The more load you put on the CPU, the more energy it's going to use. It's not like flat. So obviously, if you ask less than the CPU, it's going to save electricity. If you look at the global infrastructure, anything can prevent horizontal or vertical scalability means you're going to need more resources, or you're going to have idle servers, which is, as you see, that idle doesn't mean zero. Idle is already like something. So everything that can help vertical scalability, for example, scaling down, it's good for the planet because you will use smaller machine or reuse old machine. So an idea also could be like to compile to ARM because ARM is very energy efficient. But be careful because in that case, you will not reuse old machine because all machines are pretty new, for example, on AWS and GCP. So you need to think of all of that. So once we have like the power, how we can convert it into CO2 emissions. So there is a very handy website I use often, which is electricity maps. And you can see in real time what the carbon intensity of all the grids in the world. So as you can see, 9 of October, France was emitting 16 grams of CO2 per kilowatt hour, while California was emitting like a lot more. And Germany probably even more, depending on the day. So I know Ireland is around like the same as California in terms of the carbon intensity of the grid. So there is, you can take advantage of that first. For example, like rewriting your code with AI in a country where electricity doesn't emit a lot of CO2 and use it where you have your customer. You can think about that. So I don't want to enter into too much details for that. I have a couple of talks that are listed in this GitHub page. So if you want to know more about how you can reduce the carbon footprint of the cloud or what's the carbon footprint of AI in general, you can check this out. So if legacy code is that bad, why aren't we rewriting it into something more modern? Because like, it's emitting more than civil aviation, it's a big problem, and it has a lot of cost associated. So let's take a real life example. So I'm not a specialist of Django, so basically I've just looked at the numbers. I did not check what could be optimized, but I calculate back on the envelope, like it's not like a scientific study, but just to show like numbers. Back of envelope calculation, I calculated that Django deployed everywhere emits 27 tons of CO2 per year, 27,000 tons of CO2. So 1 ton of CO2 is around a passenger taking a flight to United States from Europe. So basically 27,000 flights to United States. So it's a lot of energy. And if we manage, so there is some studies showing that we can, if we optimize the code, we can reduce the carbon footprint by 10 or 25%, or we can optimize the energy used by 10 or 25%. So we can easily reach 4,500 tons of CO2 per year if we rewrite that. But how long it's going to take for a developer? So there is this very old book. It was written in 75, if I remember correctly. It says like a developer can write only 10 lines of code per day. So it seems not a lot, but you should think that if you are rewriting code, you probably need to read the code first, understand the code first, and probably need to fix bugs as well as you write. So basically, I think it's quite okay to think about that. So let's be unrealistic. Let's take 1 line of code per minute. So who in the room think it can write at this pace? Probably not everybody. Maybe more, maybe faster. So if you do that, 1 line of code per minute, it's still going to take 187 days for one developer to migrate or to optimize 25% only of the code base of Django to save these 4,000 tons of CO2 per year. So as you can imagine, it's just going to cost a lot of money to do that in a realistic pace, and it's just unrealistic at all. So if you take AI, for example, so let's convert those line of code into token, take 25%, and there is some studies showing like per token or per 1,000 of token, how much energy it's going to use. And you calculate with the map I was showing you before. I calculated, just to sum up, I don't have time to enter into details, but this migration, this refactoring, would take 37 kilograms of CO2 only. So AI takes a lot of energy, takes a lot of CO2, but compared to what it can be saved if you do it on purpose of cleaning up your code, it can be very interesting. So it's just 300 kilometers per car. The equivalence, but yeah, make a conclusion. So yeah, it seems like on the paper only, using AI to optimize code energetically seems to make sense. And what about the carbon footprint of a human comparatively? So there is a study showing that a human is emitting way more CO2, at least the laptop on where it's working, than an AI to produce the same amount of line of code or text. So I'm questioning this paper a lot, but yeah, you have this kind of analogy. So let's try to do it. So let's take a legacy system. So it's a code I've written myself just to have something which is 100 line of code, very small. It just calculates the prime number up to 100,000 and perform a 20 by 20 matrix multiplication. So that is a big calculation and absolutely not optimized. Like if you want to write that in real life, don't write it that way. Probably want to use parallel calculation, parallel threads and stuff like that. So if you do that, I won't run it directly, don't trust my demo. But if you do that, it's gonna take more than 2 seconds to calculate that. It's a lot, take a lot of CPU, 100% CPU during 2.5 seconds. So first, let's do what I've been told my entire life. Let's compile Python. So if you do that, it can be very efficient, like you can halve the performance. I mean, yeah, you can multiply the performance by 2, almost. And even if you're using PyPy, which is just-in-time compiler, it's very, very, very efficient. So first of all, what I will describe is not really necessary if you want to make your Python run and use less energy, but just for the crack, as I was told, we say here. So first of all, compilation saves CO2. Then I read this paper saying like Python is 70 times more using energy than C or any other compiler language. So why rewriting it in Rust? Because Rust is a little bit more new. And I don't know Rust. I know a bit of C, but I don't know Rust at all. So that's just the idea, just like taking something I wrote in Python and just translate it into a language which is, on the paper, way more efficient, but a language I don't really know. So what I used, and what probably most of us here in the room have used, let's use ChatGPT to ask that. So it's small code, so it should work. Yeah, spoiler alert, it doesn't work. It just says, it writes legit Rust code, but it doesn't work. So you need to have like a couple of interaction with ChatGPT to have at the end something which has nothing to do with the look and feel of the original code. So it's not what I wanted. So I rewrite the prompt a little bit more with more instruction. So I want to have my core functionality be preserved. I want HTML to be exactly the same, to be still embedded, etc., etc. And at the end, after 4 exchange, which is not that bad, but you still need to type and open ChatGPT, I managed to have like my Rust working and to go under 1 second. So it's good. It's exactly what I wanted. So I tried Claude, first attempt, done. Easy. So why? I don't want to promote Claude, but in that case, in that example, it works very well. And then I just, so it's not the goal of my talk here, but I try to ask Claude to optimize it. For example, do some parallel calculation, and yeah, you can optimize even better. But it's not what I want to demonstrate. It's just translating into Rust. So then, if you want to do it programmatically, so let's try that. So I've been on Hugging Face. I create an account on Hugging Face, get a token, get this endpoint, and I'm asking directly Code Llama those instructions. And let's test a little bit. Hopefully this won't take a lot of time. So here you need to inject your Python code, and so you can do like different ways to do that, but I was using like good old requests package to do that. And at the end, I still need to extract the code between the code block I instructed, Rust and Toml code block. And at the end, I have something looking like that, which is what I wanted. And then let's try to run it. It's failed. Why? Look at that. What Flask? Flask in a Rust library. Flask is not a Rust library. So basically, just like, despite the fact I say to take the equivalent library in Rust, if it doesn't exist in Rust, it just say, yeah, I'm going to use Flask in Rust. Probably exists. Okay. So let's be serious for a second. Let's go back to my good old Claude. So not targeting the chat Claude, but just the API provided by Anthropic. And in that case, the result was a little bit worse than, not as good as the chat. So I had some linter errors, but generating like a pretty good Rust code at the end. So key finding, AI chat services are better than querying directly LLM directly. It's probably because it's architectured a little bit differently, and it's actually like a multi-agent, those AI chat services. Another thing is bigger LLMs yield to better results. Yeah, thank you. Let's try to produce an AI agent. So that's exactly what I just did before, actually. I take the code, I ask AI to migrate using some two prompts, one system prompt. You are a developer, blah, blah, blah. A user prompt, please migrate to Rust this code. So this is an agent. So thank you, Mark, if he's in the room, I don't know, to have introduced AI agent before. I don't need to repeat myself. But what I actually did was not an AI agent, it's an AI plus human agent, because at the end, if it's not working, I still need to go back to my LLM or to my ChatGPT in the first example and paste the error code. So basically, I need to introduce another step to my agent, which is fixing it. You're a good developer, please fix those errors in Python. So instead of having a human in the loop, how can we do like a multi-agent where it's looking at the Rust code, produce some Rust code migration from Python, and then ask either some AIs or like plain old tool. So AI, for example, saying like, is it similar to the original code? Like, is it like the Rust code is doing what we want with Python? And then after to run some tests, run some linter and do the compilation. And if there is some error, just ask an AI to do the fix. By the way, you don't need to ask the same AI for everything like that. You can just pick the best AI for each purpose. So that's actually what I ended doing, which is a little bit more complex. So first it's analyze Claude. It's using Claude to analyze the code, just because the migration prompt started to be like very complex and very tied to exactly what was the Python code. So for example, I want to use like a web server using something to replace Flask, etc., etc. So then I ask like, what should I ask Claude AI to actually generate the prompt? So actually that's what it does. So it generates the migration prompt. And then I do some loop of verification with Claude, like look at the code, tell me if it's exactly what it's doing. Sometimes it's not, so it's fixing. And by the way, I'm using CodeLlama for fixing, just because CodeLlama is probably smaller and like use less energy. And then I did the build, did the linter, and every time I like to have a fix loop, and at the end running some test script. So let's test that. So I'm going to run and I'm going to explain in the meantime. So there is a lot of code to do that. I use LangChain to do that, so it's less verbose than coding everything manually. But basically, you have some chains, you have some in the agent. You see, it's not what I wanted to show. Yeah, workflow. Yeah, big workflow. For example, the big workflow, you can have a sequence of different tasks to do. So for example, run cargo check, run Clippy, etc., etc. And I have the prompt somewhere. I don't find them anymore. Yeah, for example, the fix prompt. Yeah, so please fix what is there. So yeah, it's all well organized by using LangChain. So let's come back to that later. So spoiler, I managed to do that. So it's generating a good Rust code with no linting errors. And I can even use CodeLlama, which is less effective than Claude, to do that. and it's working. So in terms of time, so yeah, we can build a multi-agent AI. So I instrumented it to get some metrics. So analysis, generation, and verification with Claude was taking roughly the same number of tokens, so yield the same energy and same CO2 emissions. And for fixing with Claude, it's taking a lot of CO2, almost like the same as generation. But generation with Claude, if I replace Claude by CodeLlama, for example, or StarCoder, which is even smaller, it doesn't work. Like I struggle to make it working. Verification, it's non-realistic to do it with just a code generation LLM. And but for the fix, I managed to replace it with CodeLlama, which yield to less energy use. So it's quite interesting to mix that, but you need to pick the right LLM for that. So yeah, it's been migration successful, and at the end I had, well, my Rust code, which looks like my original Python code, which is here. Yeah, it's not the same order of. Ideally, I would love to have like exactly this. No, it's not working. Ideally, I would love to have like the same order of method, the same naming of methods, but I'm not quite there yet. So yeah, big LLMs emit more CO2. More token equal more CO2. Yeah, so that's something you need to bear in mind. So if you have like a multi-million line of code project with dozens and hundreds of files, it's going to take a lot of tokens. You probably need to batch it. You probably need to work smartly with the context. So what I demonstrated just worked for the demonstration for a small piece of code. And if you take the performance results, so I did a quick performance test where during 30 seconds I hit the Python code with a request per every 10 seconds, and I do the same with the Rust. And at the end, yeah, Python is emitting. If I do the projection for a year to have like a bigger number, if I have it running for a year, it would have emitted 26 kilograms of CO2 compared to Rust, where it's way smaller. But it's not 75 as we saw on the paper. It's a little bit disappointing, but still better. But compared to the migration agent, so I calculated how much energy was using the migration agent and how much CO2 it was using. So actually, it kind of makes sense if you have this working for a year. It doesn't make sense for this demo, for example. So yeah. Can save CO2, but only if you're sure of the return of investment. That's the problem. So currently we don't have like a lot of feedback on that. So we need to make sure that if you have something which is quite simple that can be translated into Rust, and if it's big enough and running longer enough on like a web server, public web server, yes, that might work. But if it's just like try to optimize like a script for deploying something on AWS, it's probably not worth to optimize it because you're going to run it like twice a month or something like that. So there is a lot of pain to do that. For example, getting the code from the answer from the LLM. Sometimes you don't have code block. For example, StarCoder sometimes just, I don't want to work. That's what it is, what it does. Sometimes it's partial. It's just state like, okay, the code need to be changed. For example, for fixing the code need to be changed that way, and then after the code remain the same. Thank you, but that's not what I want. It's gonna be more I want to have the full code. Sometimes it's not even changing. So it takes a lot of prompt engineering, a lot of parameterization, like temperature, max token, etc., etc. So if you want to find a good hosted LLM to play, not because if you want to host it yourself, it's probably going to take a lot of CO2 just for a couple of requests. So it's better to use something which already has been hosted. You can go on Hugging Face, and you have sometimes this very interesting menu where you have inference API where you can test for free, which is what I did for most of my test with CodeLlama. And you have this calculator when provided by Ecologists, where you can select the provider, model, an example of prompt, like how many tokens you want, and it says how many energy. So it can help you like make your back-envelope calculation. So what it would take to do the full repo migration? It's going to take a lot of work, so we're not there yet. To my knowledge, there is not a lot of companies that are doing that. Sometimes they are doing that for small issues like spotting like security flows, some patterns, etc., etc. That could work, and it looks like that most of the time. You have an analyzer. Let's take the look at the dependency look at the dependency, the architecture, index all the code just for the context retriever to find where what the context can be interesting if you want to migrate one file, and then after you have migration orchestrator, it's going to migrate file by file or even chunk of file per chunk of file. And then after you have this validation fixed loop that can be automated and using like AIs or just build linters, etc., etc. And at the end, human should remain in control by writing the rules. So I don't want you to migrate that way, for example, and to control like the analyzer, for example. And at the end, the user still do the merge request. Remember that it's still your responsibility at the end to merge it. It's not like the machine is gonna work by itself. Like remember, Terminator. So what I tested so far is Claude, GPT-4 with ChatGPT, and different other with APIs. So as I discovered, like chat AIs are working better than just LLMs available over an inference API. And the bigger, the better, but it's more costly. Claude costs a bit of money. And it yields to better results, but use more CO2. So yeah, chat services seems way more complex than plain LLM. So as a conclusion, we can say that multi-agent AI can migrate Python to Rust, obviously. To do that on a full repo looks like much more complicated, but if you do a lot of small AI optimization that you will never do manually because it's going to take a lot of time and you don't have time for that, that's something I have good hope that one day we're going to have like a pipeline that will be able to orchestrate that and find like places in the code where it can be optimized or even rewritten. And it's going to be better than just one small manual optimization. Like one day you're going to wake up and say, oh yeah, I'm going to optimize this part of code. It's probably like take you a lot of time for a very disappointing result. And humans still need to be in the loop at the end. So yeah, at the end we can be able to reduce carbon footprint of software. So let's come to a conclusion.
What companies or organizations are attempting this kind of AI conversion of code to be more efficient?
To my knowledge, not a lot. So that's why with a couple of friends we decided to create our own, because we haven't found a lot. There is, however, some that are focused, for example, on fixing bugs, on finding some security flows. There is a couple for security flows. And like on the internet, you can find like people at Google, for example, they try to do what I just showed, not for code optimization directly, but yeah, it's something that's probably going to arise pretty soon.
For the code you wrote for the agents and so on, I think you said you instrumented it. How did you do that?
No, I did, I use callbacks in LangChain. So in LangChain, every time you want to call a task, you can ask for callbacks. So for example, it's going to look at the full response, and you will do something with the full response. So I use the response, the text of the response, to just get the code and fix it, build it, whatever I want. And then after you have those metadata. So it depends, like Claude have different formalism than Hugging Face API, different models, so you need to craft that. It's still not there yet. There is a lot of manual work for that, but yeah, you're using callbacks, and at the end you have the number of tokens. So I just add because sometimes you don't have the total token, so I add the input token, the output token, and then after, yeah, you go on ecologist, like I was showing before, like you pick something which is the closest of what you want to do. For example, that, you take like a number, there is not a lot of tooling for you to get the carbon, the energy and the carbon, but at least what you can say is if it's hosted in the right country, and if you're using a small LLM, and if you're using the smaller number of tokens, it's going to save energy at the end. But I wish we had like better tooling for that. And there is, sorry, just to finish, there is another project named Code Carbon and a couple others, but they are looking at the LLM running on the machine it's looking at. So it's going to monitor what's the energy used by your machine. But if you are running the LLM on your machine, so in my example, doesn't work. Yeah.